To introduce the very first speaker, Davide Bossini. So please, Davide, the floor is yours.
Okay, so good afternoon. Good afternoon, everybody. Thank you very much for the very nice introduction. And thanks a lot to the organizers for the very kind invitation. I really do appreciate it. Now, considering the audience of this workshop, I don't think I really need to spend time to convince you that it makes a lot of sense to shoot femtosecond laser pulses on magnetic materials, despite the discussion that we had this morning. This is the research field that is so-called ultra-fast magnetism. It's a broad field. So within this broad field, I would like to sketch out our experimental approach. We focus mostly on coherent effects, because coherent effects allow us, allow us to induce and even manipulate spin dynamics, minimizing as much as possible the energy dissipations. We also focus mostly with materials or on materials in which spin and charges are coupled already in the ground state. Because in this way, you have the possibility to understand whether coherent spin dynamics can be converted into coherent charge dynamics and the other way around. Now, in nature, there is a variety of ways in which spin and charges can be coupled already in the ground state of a magnetic material. Arguably, the most famous example is the connection between the bandgap energy and the long-range magnetic order, which means that the bandgap energy of a given material receives an additional contribution which scales typically in a quadratic way with the magnetic order parameter. A lot of experiments were performed back in the days with static spectroscopic methods, a few investigations with time-resolved methods. For a very long time, it was believed that this story was just a story for ferromagnetic semiconductors. That's not the case. Recently, it has been shown that any antiferromagnet that you can describe in terms of the Mott-Hubbard theory shows this property. Another example of coupling between spin and charges takes place in heterostructures. Heterostructure comprising a metallic layer and a dielectric magnetic materials. It's a really timely and hot concept and field. I have been working on this together with Chiara Ciccarelli, so today I'm not telling you anything about that. We will hear tomorrow everything and all the details about this from Chiara in her talk. So please stay tuned for that. Now, the concepts that I have been mentioning are concepts that we strive to pursue on the femtosecond time scale. And if you combine these keywords, automatically they do select the materials that we can investigate. I am talking about non-metallic antiferromagnets. So, no free electrons, no Joule heating, you have access to coherent effects. And then antiferromagnets, it has been already said, they display naturally a way faster spin dynamics than ferromagnet. When I use the word antiferromagnet today, I am really referring to the easiest possible antiferromagnet, a collinear system comprising two sublattices, which are equivalent. The total spin and the total magnetization do vanish, so we have to introduce another quantity as order parameter. And what I'm doing here is following the textbook definition. So I'm introducing the nil vector or antiferromagnetic vector here, indicated with capital L or small n. That's the vectorial difference between the two sublattices. Now, if you really strive to control with light the magnetic properties of an antiferromagnet, I do believe that here something crucial is missing. I really believe that you need something else because you need to enter a nonlinear regime of spin dynamics. Nonlinearity is a very broad word because nonlinearity describes really different phenomena. For instance, nonlinearity describes the generation of magnons and harmonic of magnons, which is a concept put forward some years ago by Professor Hubert Hooper. Nonlinearity describes also a concept which is the modification of the magnon spectrum that was demonstrated last year by the group of Stefano Bonetti in collaboration with me, as we showed that with laser pulses, we could induce a strain wave in a very thin film of garnet, 17 nanometer, and the strain wave could induce magnons and at the same way change the frequency of the magnons, increasing it up to 20% of the original value. Now, the nonlinearity that I'm going to address today is something slightly different because it's about the coupling between magnon mode in a given magnetic material, clearly coupling on the femtosecond time scale. Now, the material that we chose to do this experiment is an antiferromagnet so famous that I'm not going to spend even a single word to introduce it, because we use nickel oxide. Years ago, it was shown that optically, you can pump and probe different magnon modes in nickel oxide. In particular, a 1 terahertz mode, high frequency mode, and an 110 gigahertz mode, low frequency mode. The question that I'm raising today is the following. Can we couple these two modes coherently on the femtosecond time scale? To be completely honest with you, at a first glance, this question doesn't make much sense. Because these two modes are completely different. They are two eigenmodes of the material. We can already see this in a very visual way, in the sense that when you trigger these two modes, the dynamics of the order parameter is completely different. In the case of the low frequency mode, the nil vector oscillates in the plane of a T domain. In the case of the high frequency mode, the nil vector oscillates out of the plane of the domain. So even the way these two modes transform, really their geometries, is profoundly different. Nevertheless, that's the point that I want to address. Because, you know, pushing the boundaries between what is possible and what is perceived to be physically impossible is one of the main reasons I am paid. And to do this, I really need to introduce a novel concept that actually it is not so novel historically, but it was very well forgotten in our community. And that's the Exciton-magnon. I'm going to introduce it from the standpoint of an experimentalist. So I'm showing you here the absorption spectrum of nickel oxide in the spectral range below the band gap. So that's the near-infrared spectral range. You can see in the spectrum a particular feature comprising a peak, A, and a sideband, B. That appears in the spectrum of many dielectric antiferromagnets. It's not just a nickel oxide story. The typical interpretation of this feature is that A is an electronic transition, spin forbidden, and B describes the generation of a magnon. The reason why this interpretation was put forward is that the difference in energy between A and B, so namely this difference here, voila, matches the energy of a magnon mode in nickel oxide. The spectrum is measured as a function of temperature. So as the temperature is increased, the sideband is shifting. For every value of the temperature, the difference in energy between A and B matches the energy of the same magnon mode in this material. So if you plot energy of A minus energy of B as a function of temperature, you get straight and clean the temperature dependence of the energy of a magnon mode. That's why, very long time ago, this transition was called Exciton-magnon, and it was described in terms of two simultaneous processes. An electronic transition, spin forbidden, delta S 1, and the magnon generation, delta S minus 1, so that overall, the conservation of spins and of wave vector is restored. And light, and in particular, the electric field of light, can drive this transition in terms of an electric dipole scheme. Now, this concept is not at all something that I put forward. I don't want to get credit for it. Look at the publication. It's a very old story, well understood back then and very well forgotten. What we are trying to do now is to bring this on the ultra-short time scale. In nickel oxide, the magnon mode involved in this transition is a magnon at the center of the Brillouin zone. But that doesn't have to be the case. A few years ago, we started to work with another material, copper metaborate, in which you can find or you can observe an Exciton-magnon. And in that case, the Exciton-magnon involves magnons at the edges of the Brillouin zone. And now, that's brilliant. We are talking about a transition in the near-infrared spectral range. And here, we can generate laser pulses easily with commercial laser systems. And with something that you can purchase, you can now drive high-energy magnons in a resonant way. A magnon is, in essence, a perturbation of the ground state. And now you can drive a lot of them, because you do it resonantly, and they are the highest energy magnons. So you can perturb the ground state of your medium on the shortest possible time scale. The consequences of this unprecedented pumping can be dramatic. And we showed that a few years ago, because in this way, we took a material, we pumped the transition, and we photoinduced a magnetic phase transition in less than a picosecond, which, in that particular case, copper metaborate, implied that we could activate the magnetoelectricity. We switch the magnetoelectricity on in less than a picosecond. I'm not discussing that experiment today, because today I would like to show you something that you can do with an Exciton-magnon, which is, in my opinion, way more elegant. I would like to be able to pump resonantly and off resonantly the Exciton-magnon, so have access to the spectral range, and to measure spin dynamics in this way. So the experiment is a magneto-optical pump probe experiment in which the photon energy of the pump beam can be tuned in the relevant spectral range. This experiment is not something that I did myself. It was done in collaboration together with a group of Stefano Bonetti, AKA Il Doge, and all the measurements were performed in his lab at the time in Stockholm. Now, thank you. Our starting point was a very simple observation. We observed that in the literature, the Exciton-magnon in nickel oxide is described as involving only the 1 terahertz mode. So now the point is, if only the 1 terahertz mode is involved and we can pump resonantly and off resonantly, maybe we can amplify the 1 terahertz mode while we leave unaffected the other magnon mode. That was the starting point. I would like to show you some pump probe traces that we measured back then. In all time traces, you can see oscillations at a slow frequency, at the frequency of roughly 130 gigahertz. They're always there. In some data set, not in all of them, you can also observe a faster ripple, like in this one, on top of the slow oscillation, but not in all of them. For the 0.92 electron volt data set, here, for instance, there is no faster ripple. That's very smooth. You can understand way better the results if we take a look at them in the frequency domain. So now, we Fourier transform the 0.92 and 0.97 electron volt traces, and we realized that in the case of the very smooth data set, there is no high frequency component to the spectrum of the data. While in the case of the other trace in which the ripples can be observed in the time domain, a 1.07 terahertz component to the data appears, which is the frequency of the high frequency mode. Now, these are just a few time traces. We did measure for many more photon energies of the pump beam, and now we are in the position to extrapolate from each data set the amplitude of both magnon modes. And we can build up a plot like this one, in which we show the amplitude of the 1 terahertz magnon mode as a function of the pump photon energy. I'm going to show on the same plot also the absorption spectrum for the sake of discussion. If you pump fully off resonantly, you see nothing. Fine. If you pump resonantly, because now you're pumping in correspondence of the Exciton-magnon, which is this feature here, XM, you observe the highest signal that we could observe, which makes a lot of sense. The Exciton-magnon, as you can see spectrally, is very narrow. Our laser pulses aren't. They are femtosecond, so broadband by definition, as broad as the blue box that I'm showing here. So you cannot really see in our data the profile of the Exciton-magnon. It's convolved with a Gaussian of the width of this blue box. If you increase even more the photon energy, you can still see magnons, because, I mean, the signal is not zero, although it's coming down. Because now we are pumping the two transitions that I labeled PS1 and PS2. They are phonon sidebands. You do pump phonon sidebands, so you are still pumping the main exciton and the magnons, but you're losing energy into the lattice because you're pumping phonon sidebands. So the efficiency that you have in triggering magnons slightly goes down. If you increase your photon energy even more, you see nothing, and that's fine again. Now, what I'm showing you here is a resonant amplification of a mode. That's perfectly fine. But please, do not think this to be a purely dissipative process. What I'm saying is that it is not true that the stronger the absorption, the stronger the laser heating, the stronger the magnetic signal. It doesn't work like that. If we consider the data that we got in correspondence of the strongest absorption, so this point here, we could induce here the highest laser heating. We did observe magnons, but not the maximum signal. That's roughly 60% of the maximum. So the figure of merit is not how much the material absorbs. The figure of merit is the nature of the transition. You've got to pump the Exciton-magnon to amplify this magnon mode. Now, so far so good. But honestly, if you know what an Exciton-magnon is, and now you do know it, And if you know where it is spectrally, and now you know it, you kind of expect this trend of amplification. What we did not expect at all was the trend of the low-frequency magnon, because the low-frequency magnon is amplified as well. Now, telling you that that was a surprise to us would be true, but it would be a very strong understatement. For us, that was not simply surprising. That was outrageously shocking. And it was outrageously shocking. It was outrageously shocking because it is in striking disagreement with the literature. A few years ago, we showed that if you do a similar experiment in a material without Exciton-magnon, for any value of the photon energy, you induce coherent magnons. And the amplitude of the magnons doesn't depend on the photon energy. So it is flat. The spectral dependence is flat, and there is no resonance there. And that's exactly what we were expecting for the low-frequency mode. But that's not what we observed. So we have to put a bit more of work into understanding what we did observe. And the first idea that we had is that maybe when we pump the Exciton-magnon, we are not amplifying only the high-frequency mode, but we are also amplifying the other magnon mode. Or formulated in another way, we were wondering whether both magnon modes can couple to the same electronic transition. To understand this, we relied on symmetries and group theory. And we realized something very basic. The two modes have a very different symmetry, and we already saw this when we discussed the direction of oscillation of the nil vector. So while the 1 terahertz mode has the same symmetry of the electronic transition, and that's why they couple, the low-frequency mode has a completely different symmetry, so it cannot couple to the electronic transition. As a consequence, what I'm saying is that we can resonantly drive terahertz magnons and amplify them because we pump the resonance. But the amplification of the low-frequency magnon is a byproduct. It cannot take place in the same process. So now the problem has shifted. The problem has shifted to understanding how the amplification of one mode induces the amplification of the other one. These two modes are coupled. The question is, what mediates the coupling? Clearly, the first suggests, since nickel oxide is a strongly magnetostrictive material, is phonons. And then we looked into the spectrum of phonons. And we did realize something. There is no good phonon mode in the spectrum of nickel oxide for us. What I do mean is that we couldn't find a phonon with the proper frequency and wave vector for the frequency mixing to take place and for the conservation of the wave vector to be fulfilled. We realized then a very basic thing, an aspect about our samples. Our samples are single crystals, no substrate, freestanding. We bought them commercially. So our sample was in a multi-domain state. There are two kinds of domain in nickel low, S and T. You can forget about S if you work with optics, and that was the statement of some of our colleagues. You have to work and worry only about T domains, which look like that. We have already heard yesterday that domains are a problem, an issue. Maybe, maybe not, maybe they can be helpful. For sure, we cannot neglect them. And we believe that T domains play a crucial role in understanding how the two magnon modes couple. To show you how, or what we have in our mind, I would like to start with a cartoon. We know that we pump terahertz magnons because we pump the resonance. We pump the Exciton-magnon. For the sake of argument, let's suppose that we do so in one domain that we call T1. High-frequency magnons are kicked. Fine. Spins in the domain T1 can interact with the wall, setting in motion the spins in the wall. And once again, the problem has shifted. Now we have to calculate the spectrum of the wall. The spectrum of the walls in nickel oxide is really rich and complicated. It has propagating solution and localized solutions. I'm not going to the details, but I just would like to mention that underlying everything I'm telling you today, there is the fact that nickel oxide is magnetoelastic. The spectrum of the wall is strongly defined by the magnetoelasticity of nickel oxide. This localized solution wouldn't be there without magnetoelasticity, for instance. Among all the possible localized solutions, there is one with the proper frequency for the frequency mixing to take place. And we know that spins in the wall can interact with spins in the other domain because of exchange interaction at the interface. So there is a non-zero probability that low-frequency magnons get amplified and kicked in the domain T2. Clearly, it's a cartoon. Evidently, you can be a bit more formal than that. And what we did was writing the dynamics of the order parameter induced when we resonantly pump high-frequency magnons in the domain T1. That was the source term for the generalized equation of motion of spins in antiferromagnets, which we solved in the domain T2. You can consider all possible contributions, domain modes, high-frequency mode, low-frequency mode, but clearly what we really want to understand is what happens to low-frequency magnons in the domain T2. And it turns out that the amplitude of these low-frequency magnons is a function of what is called here A, the amplitude of the magnons that we photoinduce in the domain T1. This is just a sneak peek into the theory. All the details of the theory, the entire description, was published in a separate paper. This was developed by Helen Gomonai. And the beauty of the model is that it's very general. We use this to describe femtosecond nonlinear spin dynamics, but you can use the same formalism for linear spin dynamics in a magnetoelastic antiferromagnet, even in time scales that are relevant for transport, because the model can be extended to the nanosecond regime. Now, I show you a cartoon. I show you a very quick view in our model. The next thing that I can show you to convince you that I'm not telling you nonsense is a control experiment. My statement is that the coupling between the two modes originates only from the domain walls. So ideally, you would like to repeat the experiment in a single domain. We cannot make the entire crystal of nickel oxide into a single domain magnet because that would require a monster field. But what we can do is to make the domains way bigger, as big as roughly 100 microns, so that we can focus light, our beams, in a single domain. And effectively, we do the experiment in a single domain. At this point, we teamed up with Takuya Sato because he already possessed annealed samples of nickel oxide, and we repeated the experiment, expecting to amplify the high-frequency magnon, because the Exciton-magnon is always there in the spectrum, and expecting to not amplify at all the low-frequency magnon, which shouldn't be coupled in this case. And for once in a lifetime, I actually did measure what I was expecting, noticing that the high-frequency magnon gets amplified still, okay, and the low-frequency magnon is not amplified, so no domain walls, no coupling between the modes, which ultimately confirm and corroborates the interpretation of the results that I put forward a few slides ago. So, what do we learn from this? First of all, domain walls are not necessarily a nuisance, a hindrance that we should forget and try to get rid of. In some cases, they can enable novel functionalities, such as coupling coherent magnon modes on the femtosecond time scale, which could never be coupled in a single domain. In addition, I hope I convince you that it makes a lot of sense to look at systems in which spin and charges are coupled, because just considering only this case of coupling, this hybrid transition called Exciton-magnon, I told you briefly that you can drive a photoinduce a magnetic phase transition, and that you can couple magnon modes and even amplify magnon modes. At this point of my talk, usually I do acknowledge my collaborators. This time, I want to do this even more strongly than usual, because this project could have never come to light without the collaboration with Stefano Bonetti, and even more than with Stefano, with this postdoc who did all the hard work in the lab, so Matteo Pancaldi and Martina Bossini. They did an amazing job back then. I think they're still doing an amazing job for their project. So I also want to evidently acknowledge the funding agencies. The Cost Action Magnetophone supported the entire collaboration with the group of Stefano, and in my case, the DFG, which awarded me the Emulator grant. I would like now to conclude my presentation, thanking all of you with your attention, and looking forward to the discussion of my results with you. Thank you very much.
Okay, thank you. Thank you, Davide. Very enthusiastic presentation. The contribution is open for discussion. Any questions right away? Let me start then. So since you were talking about amplification, can you assign amplification factor to this phenomenon? Can you estimate what is the amplification factor?
Yes. I can only normalize it on the maximum signal that we have, because